4.6 billion years ago, our sun started to form about 2/3 of the way out on one of the spiral arms of the Milky Way. Our sun is a third-generation star, starting from gaseous clouds and dense nebulae containing many heavy elements. It condensed under the inexorable pressure of gravity until it was hot and dense enough to experience nuclear fusion at its core. As stars go, our sun is an average yellow star. But it is so massive that it contains 99.8% of all the mass in the solar system. Its radiant energy supports almost all life on Earth, and it drives Earth's climate and weather. It is almost 900,000 miles in diameter. It has a core temperature of about 15 million degrees, and its surface temperature of about 6,000 degrees. The sun will be fairly stable over the next 5 billion years, at which time it will enter its red giant phase. It will expand enormously so that its outer layers will reach the current orbit of Earth, giving it a diameter of almost 200 million miles. After that, it will live a few billion more years as a white dwarf. Mercury is the smallest planet in our solar system. It is only about 3,000 miles in diameter and has a surface that is pockmarked with craters like our own moon. It is the innermost planet and has an elliptical orbit that takes it within 28 million miles of the Sun at its closest approach, and out to 43 million miles at its most distant. It takes Mercury 88 days to orbit the Sun. And figure this out, sports fans. Although it rotates once every 59 days, the day on Mercury is 176 Earth days long. Oh, it doesn't really have a tail. We added the one in the video to make it easier to see and to show its orbit. And although the scale is correct for the size of the Sun relative to Mercury's orbit, we are showing the planet 100 times larger than it would be if it were to scale as well. Except for the Sun and the Moon, Venus is the brightest object in the sky. And since it is closer to the Sun than we are, it shows phases like the Moon. Shrouded in permanent clouds, Venus rotates on its axis every 243 days, and it rotates backwards from the other planets. It is only slightly smaller than the Earth, and it orbits the Sun every 225 days, at a mean distance of 67 million miles. But its surface is terribly inhospitable. The atmospheric pressure at the surface is 92 times that of the Earth, similar to the pressure a half a mile down underwater. Its temperature is a balmy 900 degrees Fahrenheit. All in all, not a good vacation spot. Our Earth is 8,000 miles in diameter and rotates on its axis, causing sunrise every day. It is the largest of all the planets that have a solid surface, and it possesses an unusually large moon for a planet of its size. Since the moon circles the Earth, we think of the moon's motion as circular. But since the Earth-Moon system revolves around the Sun at about 65,000 miles per hour, the moon's motion in the solar system isn't much different from our own. At 93 million miles from the Sun, the Earth is the third innermost planet, and is the only place in the solar system that we know of that has liquid water. Mars is the planet most similar to Earth in terms of habitat. Although smaller than Earth and Venus, it has a thin atmosphere and probably had liquid water on its surface in the past. This attracts our interest and has prompted us to send a plethora of probes. It has 2 orbiting irregular-shaped rocks graciously called moons, which are probably captured asteroids. A day on Mars lasts about 24 hours, very comparable to our own. The volcano called Olympus Mons, or Mount Olympus, is the highest known mountain in the solar system. It is an extinct volcano and is over 3 times the height of Mount Everest. Mars is the 4th planet from the Sun and completes its orbit every 2 Earth years. Jupiter is huge. If it had only been a little larger, it could have become a brown dwarf star circling our Sun. It is a gas giant and has no solid surface. Its atmosphere forms bands of poisonous clouds that circle the planet in opposite direction. The giant red spot is a huge storm that has been raging for hundreds of years. 4 of its many moons are so large that Galileo spotted them with his primitive telescope in 1610. In addition to moons, all of the gas giants have rings, but Jupiter's rings are so faint they are not visible. The 5th planet out, Jupiter orbits the Sun at a distance of 480 million miles and takes almost 12 years for one complete circuit. Notice the large separation between the orbits of Jupiter and Mars. This is the realm of the asteroid belt. It is the debris of a planet that failed to form because of Jupiter's gravitational influence. Saturn is the 2nd largest of the planets. Only Jupiter is larger. Like all the gas giants, it has a system of rings. And the rings of Saturn are glorious. Like Jupiter, Saturn also has dozens of moons, and one of them is particularly notable. Titan is the 2nd largest moon in the solar system, and it possesses an atmosphere remarkably like Earth's. It is primarily composed of water ice and rocky material. It is even possible that under the clouds and surface ice, Titan has liquid water and maybe even microbial life. It is 50% larger in diameter than our own moon and 80% more massive. Saturn takes 29 years to orbit the Sun, and does so at a distance of 890 million miles. Uranus rolls on its side. It is an icy giant of a planet, the 3rd largest in the system. Like the other giants, Uranus has a ring system and numerous moons. It is the 7th planet out, and it orbits the Sun at a distance of 1.9 billion miles. A year on Uranus lasts 84 Earth years. Because of its extreme axial tilt, seasons on Uranus are worth a look. At the time near the solstice, one pole continually faces the Sun, while the other faces away. Only a narrow strip near the equator experiences Uranus' 17-hour day. At the other side of Uranus's orbit, the orientation of the poles is reversed, so each pole gets 42 years of continuous day, followed by a 42-year night. Okay, let's head to a point high over the ecliptic, so we can see the relative sizes of the orbits of the sunward planets. Neptune is a blue world. It is the smallest of the giant planets in our system, but still 30,000 miles in diameter. Since the demotion of Pluto, it is the furthest planet from the Sun. Neptune's rings are very faint, and of its 13 moons, only Triton is massive enough to be round. It rotates every 16 hours and orbits the Sun every 165 years at a distance of 2.8 billion miles. Pluto is now deemed a dwarf planet and a member of the Kuiper Belt. The Kuiper Belt is a region of the solar system that extends just beyond the orbit of Neptune, at about 2.8 billion miles out to about 5 billion miles. Like the asteroid belt, it is crammed with many small bodies orbiting the Sun, most of which are frozen methane, ammonia, and water. Here's a size comparison. Earth, Ganymede, Titan, our Moon, and several bodies from the Kuiper Belt. Currently, the largest known Kuiper Belt bodies are Eris, Pluto, Sedna, and many more without formal names like FY9 and EL61. A day on Earth is a deceivingly simple concept. Today we'll examine that day on Earth in detail, perhaps uncovering a few surprises. A day is the length of time it takes the Earth to spin 360 degrees on its axis. Or is it 361? Here is a simple model showing the Earth, the Sun, and some background stars. The Earth travels around the Sun in an ellipse, with the Sun at one focus. The model, of course, is not to scale. Let's begin our examination at noon one day. The Sun is directly above the red line. That will be our reference point. Watching from a high vantage point, we see the Earth complete 360 degrees of rotation. But during that time, the Earth has also moved a bit in its orbit. So even after a 360-degree turn, the Sun is not directly above the same point on Earth that it was at the beginning of the spin. It is not noon of the next day. The red reference line needs to spin a little more than 360 degrees to get us to noon. The 360-degree rotation is called a sidereal day, while the noon to noon rotation is called a solar day. Earth orbits the Sun once for about every 366.26 sidereal days, and once for every 365.26 solar days. Not only that, the length of the solar day varies throughout the year, and for two different reasons. First, because of its orbit is an ellipse and not a circle, the Earth moves faster when it is near the Sun and slower when it is further from the Sun. So the little extra amount of rotation that the Earth needs to do to get from noon to noon changes throughout the year. Second, because the Earth is tilted on its axis, the little extra rotation to get from noon to noon is largest at the solstices and smallest at the equinoxes. So solar days grow progressively longer as we move from the equinox, March and September, to solstice, June and December. And did we mention the Earth's spin is slowing down? And the length of the solar day is increasing due to gravitational tides between the Earth and the Moon? The length of the mean solar day is increasing at a rate of approximately 1.4 milliseconds every century. 2 billion years ago, there were about 750 days in a year. Now let's talk about daytime. That period out of 24 hours when it is light outside. Day versus night. Due to refraction and scattering of light by the atmosphere, there can be daylight even when the sun is slightly below the horizon. But day length is usually about the sun's disk being on or above the horizon. So the day begins the moment the sun's disk appears during sunrise, and ends the moment the sun's disk disappears during sunset. At the equator, daytime and nighttime are equal to within a few minutes. But at distances north and south of the equator, the length of the day varies with the season, with the longest and shortest days being on the solstices. At the poles, once the sun has risen, it stays up for 6 months before it sets again. And during the course of each day, it travels in a complete circle around the edge of the sky. Because the Earth travels at different speeds in its orbit, the sun is north of the equator for almost 4 days more than half the year, and the length of the average day in the northern hemisphere exceeds the length of the average day in the southern hemisphere by a few minutes. In the northern hemisphere, the Arctic Circle is the southernmost latitude where 24-hour daylight can occur at least 1 day in a year. In the southern hemisphere, the Antarctic Circle is the northernmost latitude where 24-hour daylight can occur at least 1 day in a year. And daylight savings time is like the old man who cut off one end of the blanket and sewed it on the other end to make it longer. A year on Earth is measured by one complete trip around the sun. Seems simple enough, but there is a problem. The Earth doesn't travel in a path around the sun that returns to its starting point. So how do we know when a year starts or ends? Well, one way, called a sidereal year, measures our orbit against the distant stars. As viewed from the Earth, our orbit causes the sun to appear to move through the constellations of the zodiac on a path called the ecliptic. And when the sun returns to its starting point, a sidereal year has passed. This motion is difficult to observe directly because the stars cannot be seen when the sun is in the sky. However, if you look at the sky before each dawn, the annual motion is very noticeable. The last stars seen to rise are not always the same, and within a week or two, an upward shift can be noted. As an example, in July in the northern hemisphere, Orion cannot be seen in the dawn sky, but in August, it becomes easily visible. Measuring a year this way gives a period that is 365 days, 6 hours, 9 minutes, and 10 seconds long. Another possibility is to measure the year against the passing of the seasons.
Because of the tilt of the Earth on its axis, the position of the Sun in the sky changes from day to day throughout the year. If we were to take a picture of the Sun at noon regularly throughout the year, we would see the Sun moving on this path called an analemma. On the days in its orbit when the Earth is at a maximum tilt towards or away from the Sun, the length of the daylight is at a maximum or a minimum. These days are called solstices, and the Sun will be at the top left or bottom right of the analemma. On the days when the Earth's tilt is perfectly sideways to the Sun, the day and night are equal in length. These are the equinoxes,
and the Sun will be at a latitude-dependent position in the analemma.
When the Sun goes from one vernal equinox to the next, a tropical year has passed. Measuring this way gives a year that is 365 days, 5 hours, 48 minutes, and 46 seconds long. The length of a year on Earth is affected by several gradual and cyclical changes in its orbit and its tilt. First, there is the precession of the Earth's axis. Over a period of about 26,000 years, the Earth's axis traces out a circle in the sky. One result of this is that the North Star changes over time. Right now, the Earth's axis points towards Polaris. 5,000 years ago, the axis pointed to a star in the constellation Draco. And 12,000 years ago, the brilliant star Vega was the pole star. And because of the 26,000-year cycle, Vega will be the pole star again in 14,000 years. The precession of the equinoxes is caused primarily by gravitational forces of the Sun and the Moon acting on the Earth. While the axial tilt is the primary cause of seasons on the Earth, the distance from the Sun, which changes throughout the year because of the elliptical shape of the Earth's orbit, contributes a small bit of temperature variations throughout the year as well. When the axis is aligned so it points towards the Sun during perihelion, one hemisphere will have a greater difference between the seasons, while the other hemisphere will have milder seasons. The hemisphere, which is in summer at perihelion, will receive much of the corresponding increase in solar radiation. But that same hemisphere will be in winter at aphelion and have a colder winter. The other hemisphere will have a relatively warmer winter and cooler summer. When the Earth's axis is aligned such that aphelion and perihelion occur near the equinoxes, the northern and southern hemisphere will have similar contrast in the seasons. At present, perihelion occurs during the southern hemisphere's summer, and aphelion is reached during the southern winter. So the southern hemisphere seasons are somewhat more extreme than the northern hemisphere seasons when other factors are equal. In addition, the gravitational effects of other planets cause the ellipse of our orbit to slowly spin around the Sun. It takes about 112,000 years for the ellipse to revolve once, relative to fixed stars. When considered together, the two forms of precession add, and it takes about 21,000 years for the solstice to go from aphelion to aphelion. The dates of the perihelion and the aphelion advance each year on this cycle, an average of 1 day per 58 years. The eccentricity of the Earth's orbit is a measure of how round or how oval the orbit shape is. Over thousands of years, the eccentricity of the Earth's orbit varies as a result of gravitational attractions among the planets, primarily Jupiter and Saturn. The orbital eccentricity cycles with a period of roughly 100,000 years. As the eccentricity of the orbit evolves, the semi-major axis of the orbital ellipse remains unchanged, so the length of the sidereal year remains unchanged. As the Earth travels in its orbit, the duration of seasons depends on the eccentricity of the orbit. When the orbital eccentricity is extreme, the seasons that occur on the far side of the orbit are substantially longer in duration. In addition to axial precession, there's the axial tilt, the angle the Earth's rotational axis makes with its orbital plane. It is currently about 23.4 degrees and is declining. This tilt varies from 22.1 degrees to 24.5 degrees. It makes one complete tilt and back every 41,000 years. This change in tilt is directly related to ice ages on Earth. The last maximum tilt occurred in 8700 BC, and the next minimum tilt will happen in 11,800 AD. The inclination of Earth's orbit drifts up and down relative to the present orbit, with the cycle having a period of about 70,000 years. And the orbit also moves relative to the orbits of other planets as well. By calculating the plane of unchanged total angular momentum of the solar system, we can define the orbital plane called the invariable plane. It is approximately the orbital plane of Jupiter. The inclination of the Earth's orbit has a 100,000-year cycle relative to the invariable plane. This 100,000-year cycle closely matches the 100,000-year pattern of ice ages. A year on Earth is directly determined by all the various orbital motions of the Earth. So, if someone tells you how many years old they are, you might ask them, is that sidereal, tropical, or anomalous years? Want to see something really big? Well, watch this. Our starting point is our own moon. We've seen men walk on the moon, and it's pretty big. But even the smallest planets are bigger. Here are Mercury, Mars, Venus, and Earth. And the gas giants in our solar system are huge in comparison. Here are Neptune, Uranus, Saturn, and Jupiter. And of course, our Sun makes even Jupiter seem small. But let's look at some really big stars. Here's Sirius, and Pollux, and Arcturus, and Aldebaran, and Rigel, and Deneb, and Antares, and Betelgeuse. And the largest star we currently know about is VY Canis Majoris. On this scale, our Sun would be 1/10 the size of the tiny little dot you see to the left.
We know mass distorts space. We know light is affected by gravity. And we know Einstein's theory of general relativity makes possible one of the strangest objects ever imagined by physicists. If you could create a large enough distortion in space-time, by placing enough mass in a small enough space, you could create a region of space-time so strongly curved that nothing not even light, could escape it. And since nothing can travel faster than the speed of light, anything that entered this region of space-time would be trapped there until quantum mechanical effects allowed it to escape. Black holes can come in any size and have any mass. All that is required is that enough mass can be concentrated to the point where it collapses under its own gravity. Stellar mass black holes are formed when stars 20 or more times the size of our own sun finally run out of fuel in their cores. They rapidly cool and collapse, and the shockwave from the collapse blows the outer layers of the stars to bits in a colossal explosion called a supernova. But the small, dense core of the star can remain bound together by the force of gravity. As it continues to collapse inward under its own weight, the atomic particles of the core are smashed together until all that is left is a black hole. In its center lies the singularity, the mass of an entire star crushed into a single point in space. Surrounding that is an invisible shell called the event horizon. This is the cosmic point of no return. Once inside the event horizon, nothing, not even light, can escape except through quantum mechanical processes. Supermassive black holes may contain billions of times the mass of our sun. These monsters lie at the center of every large galaxy. Micro-black holes have tiny masses at which the effects of quantum mechanics are very important. Black holes of this type have been proposed to have formed during the Big Bang and would quickly evaporate due to said quantum mechanical effects. At the end of their life, it is believed that they would emit a sudden burst of energetic particles, but no such bursts have been detected as of 2008. We can never see into or directly know about what happens inside the event horizon of a black hole. In effect, any object that crosses this imaginary line has left our universe for good. But if nothing, not even light, can escape a black hole, then how do astronomers manage to detect them? It is possible to imagine spotting a solitary black hole by observing the bent starlight from behind it. But a better chance of detecting one would arise if they were not alone in space, but accompanied by another star. This black hole is drawing matter from a companion star, which orbits it at a distance safely outside the event horizon. As the gas spirals into the black hole, it heats up and emits huge quantities of high-energy radiation. Intense radiation emerging from a small area, or stars orbiting small invisible companions, these are telltale calling cards of a black hole. $12.5 billion years ago, the universe was littered with the remains of first-generation stars, and billions of second-generation stars were born from these clouds. Small groups of these new stars were drawn to each other gravitationally and merged to form ever larger and larger groups. Our own galaxy, the Milky Way, is an example of a spiral galaxy born in this early era. Today, it contains about 200 billion stars and is still growing as it absorbs small neighboring clusters of stars. The center of our galaxy is in the direction of the constellation Sagittarius. And like most large galaxies, there is a monstrous black hole at the center. The disk of our galaxy is about 100,000 light years across, and on average is only about 12,000 light years thick.
our own Sun is a third-generation star and is located about 2/3 of the way out on the spiral arm named Orion. We are about 26,000 light-years from the center. The Milky Way is a member of a group of 20 or 30 galaxies and star clusters called our local group. The largest galaxy in this group is our sister spiral galaxy, Andromeda. Is it possible for distant galaxies to be moving away from us faster than the speed of light? And if it is, would it be possible for us to see them? Surprisingly, the answer to both questions is a resounding yes. How is that possible? How can something travel faster than the speed of light? Today we will try and paint an accurate picture of the universe based on the lambda cold dark matter model, which is the best cosmological model today. Once we have painted that picture, the answers to our questions will be straightforward. Let's assert that some kind of space-time quantum foam sort of something existed before our own universe began, before our Big Bang. Then we simply let Heisenberg's uncertainty principle go to work for us. If we look at the tiniest speck allowed by quantum mechanics, a small volume with a Planck length as its linear scale, the speck would have a volume of 10 to the minus 99 cubic centimeters. And the largest amount of mass or energy that we could put in this volume without it becoming its own black hole is about 1/100,000th of a gram. Interestingly, the uncertainty principle allows this much stuff to be created out of nothing for as long as 10 to the minus 43 seconds. Not a very long time, but it will prove to be enough. Because if that much energy is created in the form of a certain type of scalar field, then we have just successfully created a universe. The best model of how our early universe grew after that initial quantum fluctuation created it includes inflation, a period when the scalar field divides space into a brief period of extreme exponential expansion. During inflation, space erupted from its tiny beginnings into an unknowably huge volume. This enormous expansion generated an enormous amount of gravitational binding energy, at least 10 to the 85th grams. And this was counterbalanced by a corresponding group of positive energy in the scalar field. What began as a mere fraction of a gram of energy has now become 10 to the 85th grams. This is a huge number, large enough to account for all the matter and energy that exists today. But notice that the total energy in the universe is within a quantum fluctuation of equaling 0. As a byproduct of the enormous growth of space during the inflationary period, tiny quantum fluctuations grew into macroscopic fluctuations in the density of the scalar field, making it ever so slightly lumpy. This lumpiness provided the seeds for the formation of stars and galaxies and all the structure we see in the universe. At the end of inflation, the temperature throughout all of space was still enormously hot. But as space continued to expand, it cooled, and the energy of the scalar field, which now filled all the new and enormously huge volume of space, decayed into dark matter and dark energy and normal matter. The photons and quarks and electrons, which in turn settle down into the protons, neutrons, and atoms that populate the universe today.
After about 380,000 years of expansion and cooling, charged particles got together to form neutral atoms. And suddenly the photons that were bumping into charged particles every second or two were free to zip unhindered across space. This is the origin of the cosmic microwave background that we see today. Let's let this volume of blue dots represent all of space at that era. Then let's focus our attention on this tiny portion that has a radius of about 42 million light years. This is the region that will be all of our observable universe in 13.7 billion years. Our Earth will form somewhere in the center of this region in about 9 billion years. But we have a lot of expansion to experience first. Imagine that you are standing on a 100-meter track and someone 99 meters away is going to walk toward you. There's the starter's pistol, and the walk begins. But there's a problem. The track is stretching, growing longer as he walks. He takes a 1-meter step every second, but the track grows 1 meter for every 100 meters every second. After 10 seconds, the walker has taken 10 steps, but the remaining 89 meters has grown so that he still has 98 meters from you. Another 10 seconds, and he's still almost 97 meters away. It will take him 460 seconds, but he will eventually reach you. And during that time, the track is stretched so that it is now 10,000 meters long. The other end of the track is now moving away from you much faster than the walker can walk. If he had to start there now, he would never get here. And the question of how far he walked is ambiguous. We could say he walked 99 meters because that was the distance at the beginning, or we could say that he walked 9,900 meters because that was the distance at the end, or we could say 460 meters because that is his normal speed times the time it took. The expanding universe exhibits the same characteristics. Light from the edges of the 42 million light-year sphere began their journey to the spot where the Earth will develop about 13.7 billion years ago. But during the trip, the intervening space multiplied itself 1,090 times. And now the spherical shell from which the light began is about 46 billion light-years away. This is the farthest into space we can see right now, and it is called our particle horizon. 100 million years after inflation, the first stars formed. They were massive giants that formed in every region of space, including our little sphere of observable universe. Those that formed on a shell a little inside our expanding particle horizon are just visible today. The light from these primitive giants has been traveling over 13 billion years. And the shell of space where they formed is now over 36 billion light years away. So light from the microwave background was emitted from a distance of just 41 million light years away. And that distance is now 46 billion light years. And light from the earliest stars was emitted from a distance of 1.5 billion light years. And that has grown to 36 billion light years. Due to the faster-than-light expansion of space in those early years, the light was actually moving away from us for billions of years before the slowing expansion allowed it to start moving towards us.
Light we see today from some distant galaxies that was emitted from 5 to 6 billion light years away comes from objects that were the most distant at the time the light was emitted. Massive objects like the Earth and the Sun, that are gravitationally bound to one another, can overcome the expansion of space between them. Space is expanding in our system, but the distance from the Earth to the Sun does not change because of this expansion. Why? Because as space expands, the Earth's orbit continually adjusts to keep the Earth at the correct distance that is demanded by the law of gravity. This is also true for stars inside a galaxy that are gravitationally bound, and is true even for local clusters of galaxies. As space expands, the distance between the bodies constantly adjusts to comply with the laws of gravity. The wavelength of light from distant objects is shifted toward the red end of the spectrum if they were moving away from us. And the expansion of space is measurable by measuring the redshift. And unlike the Doppler redshift, the cosmological redshift says nothing about the recessional velocity of the emitting object either at the time the light was emitted or at the time the light was received. Hubble's law says the further away an object is, the faster it is receding without limit. So, there are always objects far enough away to be receding faster than the speed of light. Objects we see with a redshift of about 1.46 are moving away from us at the speed of light, and all objects with larger redshifts are receding faster than the speed of light. Most objects in the extended universe are traveling away from us with velocities fast enough that we will never see them. In effect, we have an event horizon, and events beyond our event horizon are effectively unknowable to us. Objects that have a current redshift of about 1.8 are currently about 18 billion light years away, and are now crossing our event horizon, never to be heard from again. Finally, this is a time sequence of the evolution of our universe. Big Bang, followed by inflation, reheating or the birth of matter, birth and death of the first stars, and the ongoing formation and growth of galaxies. When we look out into the universe, we are looking backwards in time, looking at the universe as it was when it was a lot smaller and a lot younger.